So let's continue where we left. So the power in the spread spectrum signal that was transmitted is the same as in the original information signal dt of t. Due to the increased bandwidth of the spread spectrum signal, the power spectral density must be lower. So the transmitted signal, information signal, is narrowband signal. So when we transmit this signal over the when we modulate PN sequence with respect to this information signal, that means when we multiply the signal with the code PN sequence, then this signal will be spreaded, and the spreaded signal will have the uh, power spectral density lower because now we have much more bandwidth than in the actual transmitted signal, the narrowband signal. So due to the wide bandwidth, the power spectral density will be lower. So it may be transmitted under the noise figure, under the noise, beneath the noise, and with the right code at the receiver, it can be recovered properly. So when we do the demodulation, we receive the signal, we multiply that signal again with the code that was used to modulate the data at the transmitter to recover the original data signal. So performance in the presence of interference, the received signal RXT consists of the transmit signal TXT plus an additive interference I that include noise, other users, jammers, etc. So the receive signal is equal to transmit signal plus I, where I is the interference that include noise, other users, transmissions, jammers, and etc. So to recover the original data GT of T, the receive signal RXT is multiplied with a locally generated PN code CRT, that is an exact replica of that used in the transmitter. And these two must be synchronized. The multiplier output is therefore given by uh, Rx of t into Ct of t is equal to dt of t into Ctt into Ct of t plus I Ct of t. So the data signal gt of t is multiplied twice by the PN sequence, whereas the unwanted inference is multiplied only once. Since when we multiply the two codes, they will generate plus one, and then the multiplier output becomes gt of t plus interference into Ct of t. So the multiplication of interference I by the locally generated PN code means that the spreading will affect the interference that just as did with the information bearing signal at the transmitter. So after despreading, the data component DAT of T is narrow band, whereas the interference component is still wide band. By applying the signal to a baseband low pass filter with a bandwidth just large enough to accommodate the recovery of data signal, most of the interference component is filtered out. The effect of the interference reduced by the filtered, the large processing gain G of P. So if there is narrow band interference, as you can see in the figure, we have input data G of T multiplied with the PN code that is spreading, and the transmit data here we say TXB. Through the channel, we have narrowband interference included. At the receiver, despreading is done by multiplying the received data with the locally generated PN code and output data that may include the narrowband interference. The narrowband noise is spread by the multiplication of the PN code of the receiver. The power spectral density of the noise is reduced with respect to the despread signal. Only 1 over GP of the original noise power is left in the information baseband signal. So the wideband interference, another scenario where we interference is wideband interference that also will be spreaded, and you can see the wideband interference is below the receive signal, despread signal. So still there is a difference in the power levels. So still we can recover the required signal, but it will also have the components of the wideband interference signal. So the multiplication of the received signal, the PN code that the receiver gives a selective D spread of the digital data. The multiplexer interference signal is uncorrelated with the PN code sequence and is spread. So origin of wideband noise, multiple spread spectrum users, multiplexes mechanism. Gaussian noise, there is no increase in SNR, which is spread spectrum. The larger channel bandwidth, RC instead of RS, increases the received noise power with processing gain. So that is noise in the information signal is equal to noise power spectral density into B of W, that is bandwidth, that is equal to spread spectrum N naught B of W, that is equal to information into noise in the information signal into processing gain. So when we transmit the signal, it is actually below the noise floor. And when we recover the signal, it is quite above the noise floor and we can filter out our signal easily. So that is the beauty of spread spectrum communication. So that is a spectrum of data signal. This is a spectrum of pseudo noise signal, and that is spectrum of combined signal. User separation in direct sequence. Different users have different codes. Orthogonal means they will not interfere with each other. So user one will have different code, that is C1 of t. User two will have different code, that is C2 of t. Data will be directly multiplied with these codes. User data one will be multiplied with C1 of t, and data two will be multiplied with C2 of t. Both will be summed, and here when we have the code one will be multiplied, then when we have the integration. So the data that is multiplied with C1 of t will be again multiplied with the same code. That means that will be separate. That will be become a narrowband signal again. But the data that was multiplied with C2 of t when multiplied C1 of t will still be remain the spread spectrum or the wideband signal. So we can use a filter here and we can separate the narrowband signal, that basically the information from the user one. Then we have this frequency hopping spectrum. Hopping spread spectrum, as the name suggests here, we transmit data using different frequencies. Frequency hopping means some bits or some portion of a bit will be transmitted on different frequencies. So FH is a spread spectrum method of transmitting radio signals by rapidly switching a carrier among many frequency channels using a pseudo-random sequence known to both transmitter and receiver. So this is different from the direct sequence spread spectrum, where we multiply directly data with the PN sequence code. But here we use that PN sequence or the pseudo-random sequence PN sequence to choose a particular frequency from the group of frequencies to transmit data. A part of data, portion of the bit or full bit, depending on the speed of the FHSS. A pseudo noise sequence generated at the modulator is used in conjunction with an MR-FSK modulation. So this can be used only with MR-FSK modulation to shift the carrier frequency of the FSK signal pseudo randomly at the hopping end. So the information lies in frequency. We are modulating the frequency of the carrier to transmit our data, and that carrier frequency will be shifted from one frequency to another. At what rate we are changing it, that is known as the hopping rate. Signal broadcast over seemingly random series of frequencies. The transmitted signal occupies a number of frequencies in time, each for a period of T of H is equal to 1 over R H, referred as a dwell time. So T of H is your hopping time, that is dwell time, how much time we spend on a certain frequency. And frequency hopping spectrum divides available bandwidths into n channels and hops between these channels according to the PN sequence. So here PN sequence is a secret key that will determine how you will change, how will you move from one frequency to another. So what will be the next frequency that can only be determined from the PN sequence. So if you have this PN sequence, if anyone knows this PN sequence, then your data can be uh, deceived. Otherwise, it will not be. Receiver hops between frequencies in sync with transmitter eavesdroppers here unintelligible beliefs. Jamming on one frequency affects only a few bits or maybe a portion of a bit, depending on the hopping rate. The transmitted bandwidth is determined by the lowest and highest hop positions and by the bandwidth per hop position. FHS signal is a narrowband signal because for a given hop, the instantaneous occupied bandwidth is identical to the bandwidth of the conventional MFSK, which is typically much smaller than the wideband spread spectrum signal. Average over many hops, frequency hopping or MFSK spectrum occupies the entire spread spectrum bandwidth, WSS, because FHS bandwidth only depends on tuning range. It can be hopped over much wider bandwidth than an DSS system. Since the hop generally results in phase discontinuities, a non-coherent demodulation is done at the receiver. With slow hopping, there are multiple data symbols per hop, and with fast hopping, there are multiple hops per data symbol. So it's phased like that. Actually, at a particular time, a given transmission and frequency hopping spectrum is still your a narrowband signal, but the frequency range may be wider. So on that frequency range, from that perspective, it can be a wideband spectrum signal, but that available bandwidth or frequency is divided into different channels, and at one time that one channel will be occupied. So transmitting transmission bandwidth and the bandwidth of channel will match. Still, there will be narrowband signals. Uh, Due to discontinuities, because we are changing one frequency to another, there will be phase discontinuity. So we must have the non-coherent demodulation at the receiver, and it can be slow hopping or fast hopping. And that means with slow hopping, we can transmit more than one symbol at one particular hop. And with fast hopping, one data symbol can be transmitted through 1 to 3 hops. Typically, 2 power k carrier frequencies forming 2 power k channels. Channel spacing corresponds with bandwidth of input. Each channel used for fixed interval 300 millisecond in Wi-Fi, IEEE 8011. Some number of bits transmitted using some encoding scheme. Maybe fraction of bit that depend on the hopping rate. Sequence dictated by spreading code. So that sequence of changing from one frequency to another is dictated by the chose by the spreading code or the PN sequence. So that is an example where you can see we have 8 frequencies, and you can see a portion of a data is particularly transmitted is hopping between the frequencies on time. At time T1, F5 is used, then F8, then F3, then F7, then F4, then F6, then F2. So these frequencies are chosen based on the code that we provided there, the PN code. Every transmission will have a separate PN code, and that same PN code will be used as a receiver to recover the data in this FHSS. So terminology of FHSS, offset, this is the number of channels that are used by the system. That is the number of different frequencies utilized. As here we have 8 frequencies, those offset will be 8. Dwell time, this is the length of time that the system transmits on an individual channel. That is the length of time spent on one frequency. Like in Wi-Fi, it is 300 milliseconds. So on one frequency, 300 milliseconds will be spent. So that is your dwell time. Hop rate, this is the rate at which the hopping takes place. That is how fast the system changes from one channel to another or from one frequency to another. So that is, so if, so dwell time and hop rate will be like directly proportional. In case hop rate is fast, dwell time will be low. If hop rate is slow, then dwell time will be larger. Example of a FHSS frequency allocation of the FSK modulator or BPSK modulator, where the carrier frequency is controlled by a 3-bit PN code generator and produces the carrier frequency is shown in figure. So the control codes are given 3 bits codes. If first it is 0, then 1, 2, 3, 4, 2, 3, 4, 5, 6, 7. Like carrier frequency is 8 kilohertz, deviation output frequency 1.75, 1.25, and 0.75. Again 0.25. So the output frequency, the 9.75. So that is the information that we are transmitting. See, the first information is transmitted at 00, and that frequency is 9.75 kilohertz. Then information transmitted 1110 transmitted 6.75, and 101 information 101 code that is 7.25, and 010 8.75, and so on. So this is how FHSS works. Technical considerations: the overall bandwidth required for frequency hopping is much wider than the required to transmit the same information using only one carrier frequency. So very true, a lot of wastage of frequency in this. However, because transmission occurs only on a small portion of this bandwidth at any given time, the effective interference bandwidth is really the same. So use of the channel limit shows that the signal to noise ratio required for the carrier relative to the background decreases as a wide range of frequency is used for transmission. It is even possible to have workable system with negative SNRs, X-rays and decibel, which corresponds to wanted signals on average being lower than the noise level at any frequency. Bluetooth uses frequency hopping. So Bluetooth uses FHSS. So an application of FHSS is your Bluetooth. So the benefits of FHSS, 3 benefits of this: interference avoidance, multiplexes, and street. There may be significant interference at a few of the center frequencies, but even if we totally lose all bits during those hosts, we will be able to recover using the bits received during successful host. We also avoid being an interferer to someone else's signal for too long. 2 devices can occupy the same spectrum and operate without coordinating medium access at all. Their transmission will collide some small fraction of the time, but not often enough to cause failure, like we have in Wi-Fi. There is an advantage to switching randomly among frequencies. When an eavesdropper does not know your hopping pattern, they will not be able to easily follow your signal. So this was the original reason for the discovery and use of FHSS by actor and inventor Hedy Lamer in 1950. So FDM and FHSS, you can see the frequency sharing, bandwidth sharing. Same information is transmitted, but using different frequencies. All frequencies have been used, whereas in FDM, only one frequency is used for a particular transmission. So that is difference. This is the block diagram of frequency hopping, spectroscope and transmitter side. This one at the receiver side. Then we have slow and fast hopping. Frequency shifted every TC seconds. Duration of signal element in TS seconds. Slow FHSS that has TC is greater than or equal to TS. That means the time spent on a single frequency is greater than the signal element. That means few signal elements can be transmitted on a single frequency. Fast FHSS where the TC, that is time spent on a single frequency, is less than the signal element. That means few frequency hops can be used to transmit a signal element. Generally, fast FHSS gives improved performance in noise argument. Very true, because in case of any jamming, only a portion of the bit will be lost. One or more data bits are transmitted within one frequency hop. That is slow frequency hopping. Advantage: coherent data detection is possible. Disadvantage: if one frequency hop channel is jammed, one or more data bits are lost. So we are forced to use the error correcting course. So this is an example of slow FHSS using MFSK. That is m is equal to 4 and k is equal to 3. Fast frequency hopping, one data bit is divided over more frequency hops. Advantage, no error correcting codes are now error correcting codes are not needed. Diversity can be applied. Every frequency hop, a decision is made whether a -1 or 1 is transmitted at the end of each bit. A majority decision is made. Disadvantage, coherent data detection is not possible because of phase discontinuities. This applied modulation technique should be FSK or MFSK. So that is an example of frequency, fast frequency hopping spectrum. So that concludes this lecture. We almost completed the WC lectures are almost completed. Few lectures that we have previously covered need more detailing that will be covering in next classes. If you have question from this up to now, you can ask.